Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is ACI 318 CSAA 23.3 Concrete Design Updates in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They're both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout this presentation. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So we'll quickly go through the content that we will cover over the next hour today. I do want to begin with a brief description of the RFEM 6 program configuration specific to concrete design and which add-ons may be applicable. We'll then talk about our new design strip method. So previously in RFEM with the concrete design add-on, we had the ability to design surfaces only according to the FEA method. So now we have extended this to include the design strip method as well, which we will show in our first example today. We'll then move on to the punching shear updates. So previously in RFEM, we have always had the ability here in RFEM 6 to carry out the punching shear design, but this was always not considering the two-way shear reinforcement. So we've extended this so that now we can define that reinforcement directly within the surface at the nodes, and we'll see that with our second example. And finally, we'll move on to the nonlinear material model for reinforced concrete. So this allows us to consider the nonlinear behavior of both the concrete and the reinforcing steel within the analysis. And with our third example today, we'll take a look at that specific to deflection. So for those of you joining us today who are not familiar with RFEM and our concept, we do work with add-ons. So when we look at the base program RFEM 6, this allows us to fully model our structure. We have access to all of the materials, the cross sections, not only for concrete, but all of the other materials that we offer as well to get a full analysis. But when we want to carry out the design, for example, of our members or our surfaces, we do need the concrete design add-on. And this includes the ACI standard, the CSA, and other international standards. We also have the building model add-on. So this is going to be used in conjunction with the concrete design add-on to carry out the reinforcement design of these building specific features such as shear walls or deep beams, otherwise known as spandrels. So we won't be getting into this add-on today, but I did think it was worth mentioning. We have a previously recorded webinar that goes into much more detail that you can refer to on our website. We also have the nonlinear material behavior add-on. We'll see this in our third example today, but this is going to allow us to consider the nonlinear behavior, again, of the concrete and the reinforcing steel directly in the analysis. Now, there are many more add-ons that could be applicable that we offer, for example, construction stages analysis. We'll briefly mention today the time-dependent analysis that might be interesting for concrete design for a more detailed creep and shrinkage analysis. So you can refer to our website to see a list of all add-ons available as well as their functionality. So moving on to our first topic today. So as mentioned, we previously had the ability in RFEM and still do to carry out the surface design. So not only for slab elements, but also for wall elements according to the finite element analysis. So this is a detailed numerical method for reinforced concrete design according to the ACI, the CSA, and other standards. Ultimately, what we're going to determine for every single FE mesh element on this surface is the required reinforcement needed from the analysis. We compare this to the provided reinforcement at every FE mesh element, and ultimately what we're getting in our result output is what you see over here on the right-hand side with the reinforcement renderings, the required reinforcement with color-coded isolines. So some of the advantages related to this method is that we can consider localized effects. So if we're really wanting to get a detailed look at the required reinforcement and the design around openings, maybe specific supports, we can do so. It's also great for complex or irregular geometries. So for example, if we're looking at a concrete dome, we certainly would want to take this FEA approach. So all in all, it provides a greater customization for precise designs. Now, the disadvantage we could argue here is that it's not great for reinforcement layouts, that we have to take these color-coded ISO lines and to somehow convert them to standard reinforcement layouts that we would want to include in our detailed drawings or output. So therefore, we're excited to announce that we now offer this alternative method, the design strips. So this is a simplified approach to reinforced concrete design, where essentially we take this surface or this slab element, we divide it into strips, and these strips can be generated automatically according to the standards, or we could manually generate them as well. What's happening underneath the hood is that we're using this RFEM member type called a result beam. And a result beam is going to sum up the internal forces such as moment and shear across the width of that particular design strip. Now we can further take the design strips into the concrete design add-on within RFEM to carry out the full reinforcement design. Again, a little bit more simplified like a member as opposed to this FEA approach. So the advantages here is that it can be very efficient and straightforward for standard slab geometry. When we have very rectangular type surfaces, this could certainly be a very easy way to carry out the design. It's also widely accepted and it will produce standardized reinforcement layouts. And we'll see this in our example today, just how the output of the reinforcement can be a little bit more user friendly. The disadvantages we might want to mention here is that we assume uniform behavior across the strip width. So we're kind of averaging out or summing up those forces across the entire strip width. So we're going to ignore localized stress concentrations or significant variations in the stress distribution. So perhaps we have an irregular slab, so we're talking about areas with complex openings, complex geometry, non-uniform loading, where maybe we really need to focus on the details at some of these locations for our surface where the reinforcement needs to be looked at a little bit more detail rather than averaging out over the entire strip width. So with that said, we will move into our first example today. So I will begin here within the program RFEM and opening up the base data dialog box. This would be the dialog box that would be available when we create a new model. Under the second tab are all of the various add-ons. So essentially you're creating this custom software package that's specific for your design needs. We will be utilizing the concrete design add-on here, so it's currently activated. And then under the third tab, this is where we can set our standards. So we can generate the load combinations automatically according to the ASCE 7, the latest 2022 standard. And we will be carrying out the concrete design for this first example according to the ACI 318, the 2019 standard, but notice the CSA is also available within this dropdown. So once this information has been set, let us just do a quick model review. Looking at the materials, standard 4000 PSI concrete is applied to this general structure over here. And we have just a single surface element. We have our columns laid out for the 4000 PSI concrete, pretty uniform, pretty standard geometry here. Looking at the thickness of this surface, it is going to be 12 inches. So looking at the loadings now, just a couple of very simple loads for today, gravity only applied to the surface element directly. So we have here a dead load. It is considering that opening there in the center, 0.1 kips per square foot. And then I also have a live load applied. And rather than applying the live load to the entire surface, I did take advantage here of the loading options, new free rectangular load. So this allows me to place loads on various areas of the surface without applying it to the entire surface itself. So going into the load cases and combinations dialog box, we are generating the load combinations automatically according to the ASCE 7 with this combination wizard turned on. We can always deactivate this if we would like to manually create those load combinations. But here are the separate dead and live load cases. Notice self-weight is activated for the dead load case only. But one other thing I wanted to quickly point out here is this structure modification is activated. So this all has to do with the I-crack factor that is required from both the ACI and the CSA standards to be applied to members and surfaces. So I do go into more detail in previous webinars about this topic or just general modeling, more introductory if you are interested. Again, you can find those webinars on our website. But essentially, I have already created this I-crack factor to be applied to the column stiffness. You can see here the ACI can be selected directly from the dropdown. We also have the CSA standard where this bending stiffness multiplication factor of 0.7 will be applied to the columns. We also have the I-crack factor applied directly to the surface. ACI is also selected here from the dropdown with the bending and torsional factor set to 0.25. Okay, so now that those structure modifications have been set, we would apply them to the load cases. Under the design situations, so we will generate two design situations according to the ASCE 7. We have our factored load combinations here that will be used for the strength limit state design once we do get into the concrete design add-on. And we also have our unfactored load combinations that will be used for the serviceability design. It's worth noting that I have also activated here that structure modification for the I-crack factors only for my factored load combinations, not for the serviceability load combinations. And jumping to the load combinations themselves, very simple example today. Two load combinations with the structure modification activated here for the factored load combinations, and then the unfactored load combinations here belonging to that second design situation. So now that we have done the model and loading review, we want to move forward with the generation of the design strips. And what we need to do here is to activate a building grid. So this 3D building grid will help guide the program in automatically generating these design strips for us. And it's not to be confused here with our drawing grid that we have normally set visually here to help us with modeling. But rather, under the guide objects, you will see the building grids available here where we can right click to create a new building grid definition. Now, there are some other building grids available here that are set by default in the program, so we could certainly use and modify those, but I just created a new building grid here. So again, this is going to be in 3 dimensions, and we want to align this with the global XYZ axes here in the model. So the first grid line of this building grid in the X direction will be set at 0. And we first want to also set the origin point here. Rather than the point 0, 0, 0, I can graphically select this point in the lower left of the structure. And now we can see those coordinate points populate here. So we start off with the point 0 in the global X direction, and then I'm going to have 5 more lines spaced every 16.6667 feet. So basically you can see here these columns are laid out identically here with approximately 16.67 feet. So therefore we can create those additional lines in that direction. Same concept here for the global Y axis. Our first line will be at 0, and then we would like to have 4 additional lines at 12.5 feet. And finally, in the Z direction, we have 1 line generated at 0. And then in the vertical direction, we want 1 additional line generated at 10 feet. So I can just directly type that in here. So once we are done defining this, we see that 3-dimensional building grid laid out here. And again, this is required in order to now move forward with our second step of generating the design strips. So the design strips are created directly in the base program RFEM. We don't necessarily need the concrete design add-on quite yet to generate those. But we see here under the special objects tree, this new design strip wizard. So we go ahead and double click on this. And you'll notice that the program does ask for the building grid that we just created to be selected within this dropdown. We want to generate these design strips according to the building grid plane XY, or the plan view here looking down on the structure. And we have the ability to generate the design strips in two directions, which would certainly be something we would want to do for our reinforced concrete design of our elevated slab. But for the sake of this example, I'm only going to generate the design strips in one direction, the building grid axis X. The generated strip types will include both the column and the middle strips. So within this drop-down box here, we have the ability to generate the design strip width according directly to the ACI section 841. And this picture will dynamically update depending on which option we have selected here, but it is going to refer to the span widths in both directions, which is directly set within the ACI. We will be adding the CSA standard within this dropdown as well. Just for your information, it's identical to the ACI, but nonetheless, we will add it here within the dropdown. We can also select here based on the span width. You can see how the picture updates here to generate the width based only on the span in one direction, or we can choose user defined. So if you want to generate the same width strips throughout the structure, you can just directly input in that strip width. So moving forward with the ACI 318 today, we do want to tell the program which surface to apply this to. So we can graphically select here surface number 1 or simply type it in. We click OK, and now we see those design strips generated here. All the design strips are listed right above it in the design strips tree. So if I wanted to make any modifications to each one of these design strips, they're currently tied to the wizard. So that's why they're shown here in purple. If I wanted, I could always right click to disconnect the design strips, and that will allow me to individually modify, for example, the width of any of these design strips if I wanted to make further changes. So what's going on in the background? Well, with one of these design strips, if I double click on it, what it's essentially creating is the member type design strip here. And it's not editable. Again, that wizard has created this specific member type, but it's really doing exactly what I mentioned in the PowerPoint with the result beam. So this is another member type we offer in RFEM called a result beam. It is summing up those internal forces over the strip width and also considering the thickness of the surface here, all automated. So that's how the design strip is being generated here with that particular wizard. So if we go into the design strips dialog box here, again, these were all created by the wizard. If we wanted to create additional design strips, we could in the lower left-hand corner. This allows me to set the strip width individually. I could then graphically select the line. So we must have the line drawn across the surface to assign this design strip to, as well as the relevant surface. So that is an option here if perhaps the wizard didn't capture all the design strips that we wanted for our particular surface. So looking at all design strips at once, we're going to carry out the reinforcement design utilizing the concrete design add-on because this checkbox is active. So we then have this second tab available to us here. And this is where we set the reinforcement for both the top and the bottom of these design strips. So starting off first with the top, we can automatically determine the number of bars that will be needed at the top portion of this design strip. Perhaps though we do want to specify the bar number, so we'll select number 6s here. We also can automatically determine the spacing, and we can control here the parameters for the spacing for the program to help determine this. For example, we can set here the minimum spacing between our reinforcement to 3 inches, maybe the maximum spacing is 12 inches, and the increment is every 1 inch. And we can click OK. So that will be applied to all of our strips here. The minimum gap length. So I currently have this turned off for all of the strips, but you'll notice when I activate this that this picture dynamically updates down here. And what this means is that if the program determines for the top reinforcement, we don't need any required reinforcement from the analysis, we can actually forego that in the design. So a little bit more economical design, but you must put in what is the minimum gap length that you want to consider without having that reinforcement run across in those areas. Now, if you want continuous reinforcement across the entire top, we would go ahead and turn that off here. Now looking at all of our design strips together again for the bottom reinforcement, exact same concept here. We will select number 6s if we wanted to modify the spacing parameters to 3 inches as the minimum, to 12 inches as the maximum, and to optimize with 1 inch spacing increment, we can click OK, and I want continuous reinforcement across the bottom. So here are the configurations, and the configurations when we run the Concrete Design add-on are always applied to members, to surfaces, to design strips. We'll see this in our next example with punching shear. This is just going to be information that is specific to the standard we have selected, which is currently the ACI for the strength limit state design. And the design strips are designed here according to this first tab for members. So for example, if I'm not so interested in considering the torsional moments within these design strips, it's not so important for my surface design, we could completely turn that off here. All the rest pretty self-explanatory with code references that we can make modifications to here. Looking at the serviceability configuration. So this just has everything to do with our serviceability design once we do get into that add-on. For example, crack widths. Perhaps I don't want to calculate the direct crack width calculation according to the Gergely-Lutz equation, but rather I would just like to use the reinforcement requirements directly from the standard. We could go ahead and turn that off and leave this top option checked. Also, some limiting deflection ratios are also set here within these options. So once all this information is set, we can click OK, and we would want to jump down to the Concrete Design add-on within our table here. And under the input data, we see here the two design situations, both LRFD, where we can relate this here in the drop down to our strength limit state design, so factored load combinations with strength, and then our unfactored load combinations will be used for the serviceability design. Checking out the objects to design, by default, the program selects every object in here, assuming that you want to carry out the reinforced concrete design. That's not the case because I didn't put in any reinforcement in the members. I also did not put any reinforcement in the surface or the punching nodes here. So we're just going to design these design strips numbers 1 through 15. So we could start the calculation in the Concrete Design add-on with this button here directly in the table. I will jump to an already saved model. It doesn't take very long to solve, but just regardless of the sake of time, we'll jump over to the calculation already solved here. So once this calculation is complete, let us take a look at first the analysis. So we can take a look at our factored load combination here, the dead plus the live load. And we have a new tab available in our navigator over on the left where, for example, we can view the analysis results such as the deformation. But we're really interested in those design strips. So remember, we're technically treating these as members running along the length of the slab here. So therefore, we can activate the member internal forces for the entire model. And I'll go ahead and create a user-defined visibility here only for this top portion. So what you'll see here is that we can activate the member internal forces, such as the bending moment. So again, these bending moments are determined because they are summed up across the entire strip width. So it's real easy now to determine here the total internal forces from this analysis of load combination 2, kind of represented here as a member along the design strip length. We can also take a look at the shear forces, and as expected, we have higher shear forces maybe where these columns are located or at the opening edges, but again, summing up those internal forces across the design strip width. So now we would like to turn to the concrete design results. So in our navigator, we can use this drop down. So not only are we interested in the analysis, but now we turn to the actual design according to the ACI standard. So under the concrete design table, we can view the design ratios on the design strips themselves. And what we will see here in table format is we certainly do have some design strips that have some failing checks, and no surprise, it's the shear strength, pretty close to some of where these columns are located. This is actually something that we would address later on when it comes to the punching shear. So these failing design checks are nothing to be concerned with now, but rather we'd be more interested in maybe the flexural design checks that are also given. So with each design strip, as we can see, the program will kind of highlight which one we're currently looking at. We can always access the design check details. With the design check details, we can zoom in here. This is going to show us the formulas line by line and ultimately how we have calculated this design ratio for this particular strip. All the information is also shown in table format, and we can even pull open a cross-section view here of that strip to view the reinforcement at the top in tension, and we can also see the reinforcement at the bottom in, the reinforcement at the top, yes, in tension, the reinforcement at the bottom in compression at this particular area likely located over our column. So that's a little bit about the table options that we can view here for our results of the design strips. Keep in mind that everything is also visible to us here graphically. So we can activate here the strength limit state checks directly within the model here to see the design ratios along each one of these design strips. We also can view here the reinforcement. So again, referring back to the PowerPoint, this was a huge advantage of the design strips over the FEA is the output of the reinforcement. So let us take a look at what this looks like both graphically and in table format. So rather than viewing the design checks here, I'll go ahead and turn those off and we'll rather focus on the reinforcement. So if we activate the reinforcement here, and I'm actually going to choose one of these design strips and we'll choose the visibility based only on this particular design strip here. And let me cancel out this visibility. We'll try that one again. Okay, so what we will see here for, and it's still not activating, give me 1 second. What we want to see here is the required longitudinal reinforcement specific for this design strip. So we can also jump down to the reinforcement on the design strips in table format. And the one that I'm most interested in is number 14 here. So with this particular design strip running between these two columns, we can activate the required longitudinal reinforcement for the top of this design strip. So we can see here based along the length what the required reinforcement is. And with that, we can overlay here the provided reinforcement. So the whole goal is that we have the provided reinforcement is greater than the required reinforcement. And in table format, under the reinforcement on design strips, we can see here that 7 number 6s are provided for this particular strip. Taking a look here at the bottom reinforcement instead. So again, we see the required reinforcement from the analysis displayed graphically here for design strip number 14. And we want to overlay on this the provided reinforcement This is also 7 number 6s that the program has determined. We can see that this value is greater than the required reinforcement. So everything looks quite good here. Again, if we cancel out of this visibility mode here, we're going to see all of the number 6 bars, the numbers, the spacing that has been generated by the program automatically with the strip design. Also, material takeoff is available in this table format that we could export directly to Microsoft Excel with this button here. Okay, so that is a general overview then of the new design strips and how we can carry out the design according to the ACI or CSA standards. We're now going to turn to our second example to discuss punching shear. So with the punching shear design, we are referring to the ACI 318, section 22.6 for two-way shear strength. When it comes to the CSA, we're referring to clause 1332 for one-way and two-way shear. So as I mentioned earlier, we have carried out the punching shear design for quite some time in RFEM and the concrete design add-on, but we were only able to do this without the shear reinforcement considered, without that two-way shear reinforcement. So we would just flag you as a user if the strength of the concrete alone was not sufficient, but had no way to really address that further without the input of the shear reinforcement. But now we have that ability to define that here at the punching shear nodes. The reinforcement options do include vertical bars or stirrups, but we also have the headed shear studs, and we'll continue to add more options within the reinforcement dropdown that we'll see in just a minute in our example. The punching shear design is carried out for columns that frame directly into our surface or walls. So the wall ends can also be considered for punching shear. What we'll see now in our design check details within the concrete design add-on is that we have extended the punching strength design checks that not only are we going to calculate without the shear reinforcement, but we'll see the additional calculation now if we define that reinforcement with the reinforcement considered directly. We also have additional checks for the reinforcement limits and the details. So we can jump to RFEM again and get into our second example. So this is going to be just a general concrete structure here. I did want to point out though that for this example, we will be designing it according to the CSA standard instead. We're using metric units. So both are interchangeable here with ACI versus CSA. Same concepts can be applied. Looking at the model, I did want to quickly review the materials. So we have 40 MPa compressive strength defined for all of our surfaces, our wall elements here, and our columns. Looking at the thickness of the top slab here, this is going to be 250 millimeters thick. You'll also notice that within the modeling workflow, we have a lot of strange symbols shown here. So I wanted to clarify what those are. So we're actually going to be moving forward with the surface design as well, according to the FEA approach. And actually, this is required. We can still do design strips, but we'd also need to carry out the FEA approach when we are carrying out punching shear and not necessarily the design, but we do need to input in the reinforcement. And this will all make sense as we move through this example today. But because I'm going to carry out the design according to the FEA method of this elevated slab, inevitably we're going to have what we call singularities. And singularities are not unique to RFEM. They happen in all FEA programs. And the reason why is because we have these column elements, for example, that are framing up into the 2D surface, and all forces are being transferred at this single FE mesh node. But we know in reality, we're certainly getting better load distribution than just that single mesh point because our column is certainly going to have dimensions here. So what tools do we have in RFEM to address these singularities? Well, the first thing that I did is I selected multiple nodes at once. And if we double click them here, I've added in a mesh refinement. So we have the ability to add in mesh refinements for different objects in the model, including nodes. And we can take a look at here that I applied this single definition to multiple nodes where I have a radius set. I have an inner target FE length of 0.05. The outer is zero point 0.2. And again, those were applied to all of the top nodes that you see here with the symbol shown. What else you will see is the symbol shown here at the wall edges as well as the columns that are called our surface result adjustments. And these are given here under the special objects tree. We can see the surface result adjustments listed. I just created one definition type to begin. This allows me to average out or to smooth out the internal forces over a set dimension here. So this is actually considered when we take this into the concrete design add-on, that we can average out the moments, the shear forces, whatever we want over this dimension of 0.75 meters by 0.75 meters. Again, this just helps with those non-realistic singularity issues where these elements are framing into the 2D surface. So we create one definition and it can be copied multiple times to different locations here on our elevated slab. If we're curious to see the generated mesh, we can go ahead and calculate that quickly. Again, taking into consideration the FE mesh refinements, we see everything is generated by the program automatically and where those FE mesh refinements are taken into consideration. So I'll go ahead and turn off here under the types of nodes, the mesh refinements. I'm going to also turn off the surface result adjustments and the mesh all graphically, just so that we get a nice clear picture here of the model within RFM. The final thing to quickly cover is just the loading. And this is really identical to what we saw in the previous model. We just have a simple dead load applied here of 3 kilonewtons per meter squared. And then I also have a live load of 6 kilonewtons per meter squared, again, applied to the entire surface here. The load combinations are generated according to the NBC standard. We have here our factored load combinations in red. We have our unfactored load combinations in green. That I crack factor was also applied to this structure. So again, no need to review that again because it is the same as example number 1. Now we have activated the concrete design add-on. So when I double click on this elevated surface, you can see here the design properties is activated. We will carry out the design of this surface, which gives me some additional options here to input in the reinforcement directly for this elevated slab. So again, I'm just going to briefly cover this. The previous webinars will go into much more detail on how to define here member and surface reinforcement. But as a brief overview, we can input in the concrete cover, and then you can see within the drop down here, I have applied this reinforcement. So again, kind of taking this FEA approach rather than the design strips. We have 25 bars spaced at 0.15 meters for both top and bottom and in both transverse directions. This is applied to the entire surface here. The reinforcement type is set to rebar, but we also offer the welded wire mesh options. Stirrups are also available here, but I think most of us try to avoid the stirrups with any type of surface design, and we will address the shear in this example a little later on with the two-way punching shear reinforcement that is not defined here within the surface. So again, this is strictly for the surface element itself. So now that we have input in that reinforcement, let us take a look at these nodes at the top level. So when I highlight all of my top level elements here, including the nodes, I can double click them and you can see that this is where we can consider the punching shear, is with the node directly. So the program allows us to activate here the punching design, again, utilizing the concrete design add-on. And under the concrete design, this is where we can define our reinforcement. But I first want to carry out the design without any two-way shear reinforcement. So I only want to look at the strength of the concrete first. Then under this fourth tab, we do have the configurations. As I mentioned, this is very similar to the design strips. Every element that we design will have its own configuration settings, including punching shear. So what is worthwhile looking at here for the punching shear is that this top section just asks us, what do we want to use for the punching load? So for example, the columns. Do we want to use a single force, or maybe do we want to smooth out a shear force over a defined perimeter area? But we'll go ahead and just use a single force from the column. Same concept here with the wall. We will smooth the shear force over this defined area. Down here at the bottom, though, this is also worth discussing further, which you can see that these options have a nice long note here to really explain exactly what you're setting. So in our model today, we have a 3D structure. We have modeled the columns framing up into the surface. We've modeled the wall elements. So therefore, the program has the intelligence for the punching shear design that it knows the dimensions of the column framing up into the elevated slab. It knows the dimensions of the wall element. If we were modeling here instead a 2D slab element, so we just have our slab element directly modeled in RFM and we're representing our columns with nodal supports or our walls with line supports, then we would want to take advantage of these settings down here at the bottom. This allows us to input in what is the dimensions of the loaded area for the punching node type column, or if, for example, the wall element, we would need to give the wall thickness. So it's only if the program doesn't know this information from the 3D model. If you do have a 3D model and you activate this information and input this in, it will override what is modeled here back in RFM. So it won't necessarily refer to the physical object, but rather it will refer to these user-defined options here. But because we have a 3D model, we'll go ahead and leave these options off for today. So once we are done with these configuration settings, we are now ready to carry out the design. So we'll go ahead and click OK through these dialog boxes. And under the concrete design here, exact same workflow as what we saw before. We're relating our factored load combinations in that first design situation to the ultimate limit state design according to the CSA. And we have our serviceability or unfactored load combinations for our our serviceability design situation for our serviceability limit state. Under the second tab, again, the program just assumes we want to design everything. We don't want to design the members here. I'm not designing all surfaces, but rather I only want to design surface number 4. And I don't want to design all nodes. Rather, I'm going to graphically select here only the nodes that are located at this top elevation. Okay, so now that this input is done, we can go ahead and run the design. So notice that the program will go ahead and calculate the load combinations for the analysis back in the main program first. And once it's determined these forces, we go into the concrete design add-on to carry out the CSA design checks for both this elevated slab, according to this FEA approach, as well as the punching shear checks. So we will now be presented here with our results, and we can jump down to the design ratios on the surface. I think it's worthwhile just comparing this quickly to our previous example that we did with the design strips. So I'm going to activate here the required reinforcement of my surface. So when we drop down to the design ratios on the surfaces, and you can see here the different design checks that we're carrying out in comparison to the design strip. So it looks a little bit like a longer list here for our strength, serviceability, and detailing checks. Again, for each one of these, though, we can always access the design check details. And because we're not taking this simplified approach, but rather this more precise approach, which I think is pretty evident with the equations that are shown here within the design check details, but ultimately we can see how this design check ratio was calculated for this surface element for each one of these checks. And again, no surprise, we have some failing checks here at the column. So we are checking one-way shear for the surface elements at these columns. And this is, again, nothing to worry about right now with the surface because we want to alleviate this with our two-way punching shear checks with our nodes that we have just input. But when we look at the required reinforcement of our surface element that we can activate graphically within the concrete design add-on, we can see the required reinforcement with these colored ISO lines for the top direction in the global X axes, in the global Y axes, also the bottom reinforcement. So you can see how this can certainly be an advantage for a much more precise, detailed calculation for the required reinforcement of our surface in comparison to the design strip. So I just wanted to quickly mention that before we move on now to the punching shear. So with the punching shear, we will go ahead and take a look at here under our table options, the design ratios on the nodes. And we'll go ahead and expand all the options here. Maybe I select only this top surface and we'll turn this into elevation view or plan view here. So with our punching node design, remember we're carrying out the design here at every single node location at this top elevation. Well, looking at the design ratios, so you'll see here these for each one of these nodes, which the program will give you a nice arrow here showing you exactly which node you're looking at. We are carrying out the two-way shear strength as well as some additional checks. And you'll see here that we are actually failing for some of these two-way shear checks. Well, when we go into the design check details, we can take a look at in more detail exactly why this particular check is failing. And in this instance, the strength of the concrete is not sufficient for these shear forces. So this is where it would flag us that, okay, we do need to consider some additional two-way shear reinforcement. So some of these nodes are passing. If we wanted to filter here to only the design ratios that are greater than 1.0, we can see them listed here. So 4 different nodes. So what I'd like to do is to take these 4 nodes and I'll go ahead and highlight them here and we'll create a visibility by only these selected objects. Now they're currently selected in the model here. They're a pink color, but I know that's a little bit difficult for you guys to see. If I double click on one of those nodes, you can see that the 4 that are failing are selected within this dialog box, and we're going to revisit the concrete design punching node tab here. So instead of no reinforcement defined, this is where I am going to input in additional two-way shear reinforcement. So the first input in here is to select my material. Now, in this case, I've already defined here the reinforcing material, but forgot to mention this. It's always possible here to visit our material database to filter to the reinforcing steel for either the ACI or the CSA standard, or you can create your own reinforcing steel as well. We will choose number 10 bars. And then over on the right is where we select the type of reinforcement. It can either be vertical or it can be the headed shear studs, which is what we'll use for this example. And as I mentioned in the PowerPoint, we'll continue offering more options in the near future with this drop down. Under the second tab for placement, we do need to define here the number of perimeters. And I will also say that all of this input here is clearly stated with this picture over on the right-hand side, so you know exactly what information you're setting. But we essentially need to set the number of sets of reinforcement here extending from the face of the column. So we'll go ahead and increase that to 8. The number of headed studs in each direction for one perimeter. So this is by default set to 2, but we could certainly increase that if we had additional headed studs, again, extending from each face. The perimeter spacing can also be set here. This can be just a factor as a function of the surface thickness itself, or we can manually set that here, which is what I'll be doing today. So the first distance is S1. This is going to be the distance that's away from the column support face to our first shear reinforcement. It's going to be 70 millimeters. And then the additional spacing between perimeters will also be 70 millimeters. And so now our input is done here within these particular nodes. So we'll go ahead and click OK. And I do want to turn on here up at the top the display of my punching reinforcement. So now we can see graphically this punching shear displayed only at those 4 nodes that I've added this to. And the program is intelligent enough to recognize the edge of slabs here. Or for example, if we look at this wall element, it also recognizes that we only need the shear in 3 directions. Alternatively, if we were to place shear reinforcement at this single column here, we would see that extend in all 4 directions. So now that the input for the two-way shear is carried out, again, directly through the nodes, we want to redesign here within the concrete design add-on. So I'll go ahead and run this calculation. We don't need to rerun the analysis. So those analysis results are already set. The only thing that we're doing now is considering this two-way shear reinforcement for our punching shear checks. Now that this is done, I will also mention too that if we look at the design ratios on the surface, this is unchanged. We still see these high design checks here where the column is framing into the surface itself. Again, this is one-way shear that it's checking. We do plan to link the punching shear results with the surface results so that the punching shear will supersede these one-way design checks, and we may no longer see that failing check here. So they're not quite linked yet, but that is something that we plan to do in the near future. Okay, so let us drop down now to the design ratios on the nodes, and what we should see now are all of our ratios are now passing for each one of the nodes that we have designed here at this top location. If we click here graphically to this particular node, which includes the column framing in at the edge, we can see that what previously was failing for this two-way shear strength check is now much lower. 0.218. So perhaps we could optimize our shear reinforcement further to get a little bit higher design check. We can also visit the design check details here. So we still will carry out the design without the shear reinforcement and give you this information. But now we're seeing all of the additional design checks here, including the shear reinforcement. And the program will eventually output here our controlling design check being the minimum of these. So everything looks good there in table format. We also want to take a look at here in plan view, and I'll go ahead and turn off the punching reinforcement. That back under the results in graphical view, rather than looking at the design checks, which we certainly could activate here for punching shear, let me create a user-defined visibility for only this top surface. And we want to display here the reinforcement on the nodes that includes the punching shear. So here is the required reinforcement from the analysis that the program's telling you that at these 4 nodes, which we were already aware of, we need additional punching shear reinforcement. Well, then we can toggle to here the provided punching shear reinforcement. And as we'd hoped, the provided is greater than the required, which is why we are now passing these design checks. There are additional design checks here beyond the two-way shear strength that are going to utilize the longitudinal reinforcement that we set for our surface. So this is why I mentioned we input in the surface reinforcement at the beginning of this example, because that reinforcement is also used for punching shear checks. And we can see all of those available here in table format. But looking at the required longitudinal reinforcement here for punching shear in both directions at the top of our slab, we get the required reinforcement in color-coded ISO lines here also for these nodes. And if we toggle here to the provided reinforcement, we want to ensure that this is greater than the required longitudinal reinforcement. If it's not, then we would want to go back into the surface element directly and maybe specify additional longitudinal reinforcement only at these locations where we're carrying out punching shear. But I thought that was worthwhile just to mention here that that's also important. Okay, so for our final quick example here, we will go into the nonlinear concrete analysis. The nonlinear material behavior add-on is needed, and this allows us to consider the nonlinear behavior of both the concrete and the reinforcing steel within RFEM. So when we activate this add-on, we now have the ability to modify this linear elastic material for concrete to now this nonlinear damage material model. And we have a few options for the stress strain diagrams. The first is that within our dropdown, which we'll see in our example, we can select the ACI 318 for serviceability, or we can toggle this to the user-defined parametric input, perhaps if we were carrying out the ultimate or the strength limit state, interested not only in deformations, but how our internal forces would change. You can see here the stress strain diagram that's available for the ACI 318. We would also utilize the user defined for something like the CSA standard. So these standards are not so clear on nonlinear design approaches. So this is why we also offer this user defined parametric input for you as a user to define here the stress strain diagram directly. Now, when we talk about the reinforcing steel, a little bit more straightforward, we convert this to a nonlinear plastic material model. We can see the stress strain diagram shown over on the right. Now, it's also possible to consider long-term creep and shrinkage for our concrete. This is actually independent of the nonlinear material behavior. This is already available with the concrete design add-on directly. The time-dependent analysis, though, gives us further options with creep and shrinkage. We're not getting into that today, but there is a good knowledge base article that I've linked here directly in the PowerPoint that will go into more detail about creep and shrinkage and what this TDA add-on may be able to offer you. So going back to RFEM then for our final example, we have here just a general surface element, and this should actually look quite familiar. This is the same as example number 2, but I have only modeled the surface element itself. And what you'll see here is I'm representing the walls with a line support. And a cool feature in RFEM for our line support option is we can go ahead and set here a stiffness via fictitious wall. So under this second tab, we can input in the wall dimensions, the wall material, how it's connected to the surface, and the program will automatically calculate the support spring stiffness for these various degrees of freedom and apply that directly to this line support. It's the exact same concept here for the nodal support. So I haven't actually modeled these columns here in the program. Rather, I utilize this stiffness via fictitious column. And sure enough, here I have the ability to define the dimensions of the column, the material, how it's connected, and the program automatically calculates these stiffness parameters here for the nodal support degrees of freedom. So just a nice feature, again, if we're carrying out 2 dimensions here rather than modeling all 3 dimensions. This particular example, we moved back to the ACI and imperial units, but again, everything is possible with the CSA as well. So to begin, we have just a linear elastic concrete material here, 4,000 PSI. I do have reinforcement grade 60 linear elastic material as well, and the thickness of this particular surface is 10 inches. I also have the concrete design add-on activated where I have a surface reinforcement input in here. So this is going to be number 6s at 6 inches on center in both directions. So If we go to the nonlinear, to the base data here under our name of our model by right clicking, we have under the add-ons the nonlinear material behavior. So we'll go ahead and activate this add-on within the model. Maybe just quickly to mention too, before we get into the materials, just quick loading. Again, this was identical to the previous example, just with a simple dead plus live load. We also have just only the unfactored load combinations considered here for deflection checks. So now that we have activated here the nonlinear material model, we're going to take a look at here only the materials under the material dialog box. So we can go ahead and edit those. And we have here the 4000 PSI concrete linear elastic. So what I would like to do here is to make a copy of this. And because we've activated the nonlinear material, we now have the anisotropic damage material model available to us. And so now we get some additional tabs here that we can run through. So as I mentioned in the PowerPoint, this is where we define the stress strain diagram. Now we currently have this set to the SLS, referring to the ACI 24.1, but we can also modify this here to the parametric input. So again, if the standard is not very clear for maybe some of the calculation, the nonlinear calculations we want to carry out, we could utilize the parametric input instead. And we also have the ability to directly define here the stress strain diagram. So with the SLS option, according to the ACI, we're going to go ahead and leave these as the default options shown here, but of course we'd want to modify them specific to our material. Notice we can consider the tension stiffening, or we can turn this off, and this diagram is going to update accordingly. Under the stress strain diagram, this is where we can see these values output in table format. And we can also hold the control key down on our keyboard and use our mouse wheel here to zoom in to our diagram if we'd like to see this information in more detail. The time-dependent properties. So again, we can account for creep here or shrinkage. This is not needed necessarily within the nonlinear add-on that we just activated. It is available for these general concrete materials, but that TDA, the time-dependent analysis add-on, we're not utilizing for today, but certainly again, refer back to that knowledge base article for more information, but just a simplified approach to consider creep here. So going back to the steel design, the steel material, we want to also make a copy of this one. And instead of the linear elastic material for our steel, we want to modify this now to the plastic material model. And much more simplified than the concrete, we have our stress strain diagram here with the yield strength set to 60. So when I click OK, you'll notice that these two newly defined nonlinear materials are blue because they are not applied to the model yet. Rather, we're still utilizing these linear elastic materials. So going into the load cases and combinations dialog box. Again, I've deactivated my factored load combinations. We're only looking at my unfactored load combinations. And I'm going to go ahead and rename this one to ASD linear. I'm going to make a copy of this, and I'm going to rename this here nonlinear. And again, identical load combinations, but one thing that I want to do with the nonlinear load combinations is to come into the combination wizard options and make a copy here, because this is where I want to activate a structure modification. And this should sound familiar because remember, this is where we applied the I crack factor back from examples 1 and 2. But this time, this allows us to activate here the surface reinforcement directly within the analysis. So previously, without activating the structure modification, you can't consider the surface reinforcement in the analysis. But with this change, we can now do so. So once this definition is set, we want to make sure that it is selected here from the dropdown. And we also have this tab here, the selection option for different materials. and we get a new tab. This actually allows me to swap out materials for specific load combinations only. So in my nonlinear load combinations, I'm going to take that linear elastic material and I'll swap it out here for the nonlinear concrete material. And my linear elastic steel, I'll go ahead and swap this out for the plastic material model for steel. But for my linear load combinations, I'm still going to use the linear elastic material. So this is a really cool feature in the sense that we don't even have to use it for something so complicated as nonlinear. But let's say we're trying to compare a structure of 4,000 psi concrete versus 5,000 psi concrete. We can actually swap out those materials for only some load combinations versus others, compare the results without having to build two separate models. So that's the purpose of this checkbox here. Under the load combinations now, we can go ahead and toggle to this. We see here our linear load combinations listed, and then we also have our nonlinear load combinations with that structure modification set. The additional thing that we need to make here is the static analysis change to take into account that creep that I have just activated for those nonlinear materials. So when this is done, we can go ahead and click Calculate All, and the program will cycle through both our linear analysis as well as the nonlinear analysis. And what we can compare immediately is the global deformations. So when we turn to the dead plus live load here, we see the max deformation of our slab as 0.183. But then we can drop down to toggle to the dead plus live for the nonlinear load calculation. And we see here a new deformation of 0.417. Again, considering the reinforcement in the analysis, considering the nonlinear behavior, the creep, you can see how different our deflection could look for those analysis results. Now, currently, the nonlinear capabilities of the concrete is not linked quite yet to the concrete design add-on. It is only used for analysis purposes, but we'll see in just a minute some of the future developments that we do have planned for the program RFEM and the concrete design. So we'll go ahead and conclude our webinar today just to briefly mention some of the future developments. So we will very soon release the design strip twisting moment consideration MXY. So currently those design strips are only considering moment in the one direction, the length of the strip itself, but we will have an additional option to also factor in the twisting moment. Again, that's a high priority that will be released soon. We also want to integrate, as I mentioned, the nonlinear concrete analysis results with the concrete design add-on, currently only available in the base program RFEM for the analysis only. So switching gears away from kind of the add-ons that we talked about today, we are also working on the foundation design add-on. So isolated foundation design for ACI is currently in development. We hope to release that a little bit later this year. The CSA standard will follow, as well as additional foundation types later on. You also can consider the pre-stressing effects in the static analysis with the tendons add-on. This is a beta version, so if you're interested in testing that out, again, not linked to concrete design quite yet, certainly do so. And also advanced ACI 318 seismic design checks. So we're talking about strong column, weak beam. We do give some seismic design checks now for detailing, but this will certainly dive into more of those strength checks for seismic. So if you liked what you saw today for reinforced concrete design or any other material or topic that's available in RFEM and you're interested in discussing with us further, it would be great if you reached out to our sales team. You can find this with the QR code here that takes you directly to the website, and also our information in our Philadelphia office is shown at the bottom of this page. We could set up a quick online meeting with you to discuss further. We will have many more upcoming webinars. You can register at diddlyweld.com under support and learning webinars. As most of you know, I tend to send out a reminder email before these take place, so keep an eye out for that. PDH certificates will automatically be emailed to all participants who are here for the full presentation. This is a requirement of the states that we are pre-approved providers, that you are here for the full duration of the webinar. If you watched with a colleague or in a conference type setting and you yourself did not sign up and you were here for the full presentation, go ahead and request that PDH by sending us an email to info-us@dlubal.com. Just let us know who you watched it with, and we'd be happy to provide PDH for you. This is not instantaneous when the webinar ends. It does usually take 1 day or 2 days to get those to you, so you can keep an eye out for that through email. And with that said, I want to thank everyone for attending, and as always, we hope to see you at the next presentation. Thank you.